Hello, student. Uh, Today in this session, I am going to explain uh, the construction and working of the simultaneous analog to digital converter. In the earlier sessions, we have seen the importance of analog to digital converter and uh, which are the types of converters available and how they work. So in this session, this simultaneous analog to digital converter is one such converter so that can be used to convert an analog signal to a digital signal. The simultaneous method of analog to digital conversion is based on the use of a number of comparator circuits. So this comparator is an op-amp based electronic circuit that is used to compare the strength of the two signals. So one such a circuit which implies three comparators circuits is as shown below. So here is one such circuit. So this is a circuit which implies the comparators for the conversion process. And this is actually the half of the actual converter circuit. The full block diagram of this converter circuit I will show you later. So these C1, C2 and C3 are the comparators. This is the comparator 1. This is the comparator 2 and this is the comparator 3. And they have the two inputs. They have each comparator are having the two inputs. One of the inputs are joined together for the supply of a common analog input voltage, whereas the other input of each comparator is given to some reference voltage. So here, for example, C1 is given a reference voltage of V by 4, and this C2 is given a reference voltage of V by 2, and the C3 is given a reference voltage of 3V by 4. So this V can be any given voltage. It may be 5 volt or 10 volt like that. So that voltage is divided into different levels, and the different reference voltage levels are supplied to the one of the input of the comparators. So the analog signal to be digitized serves as one of the input to each comparator, and the second input is a standard reference voltage which comes from a standard reference source voltage, and the reference voltage is used here are V by 4 plus V by 2 and plus 3V by 4. Three voltage levels, four voltage levels are constructed here, and the system is then capable of accepting an analog input voltage which is lies between this 0 and plus V. So this is the comparator circuit. Means this is the half of the complete converter circuit. So here we have shown only the comparators, how they are connected. So here we are getting the outputs from these three comparators, and they are further given to the next level of circuit. So in the figure B, this is the figure A. In the figure A, this is the figure A. I have shown the comparators connections, and in figure B, I am giving here a table of the comparator outputs. Means at different input voltages, these different three comparators works. And when they work, that depends upon this voltage levels. Depending upon the input voltage, these three comparators will be either at a high position or at a low position. And so if the analog input signal exceeds the reference voltage to any comparator, that comparator turns on. That is, the output of the comparator goes high. And now, if all the comparators are off, the analog input signal must be between 0 and plus V by 4. This I will show you with this diagram. So here we have written plus V by 4. Reference voltage for this comparator C1 is plus V by 4. That means when the voltage, input voltage, analog input voltage exceeds this plus V by 4, then only this comparator C1 goes high or it starts working. Otherwise, it doesn't work. So that is the meaning. So, and all the comparators are on high position means are at on position means this voltage, input to analog voltage, should be greater than this plus 3V by 4. Then only the all three comparators goes high. And suppose if the analog input voltage strength or level is below this plus V by 4, then all these three comparators will be in a off condition. No comparator is going to work. So that is why the strength or the voltage, input voltage level is very, very important. Depending upon the magnitude of the input voltage, the different comparators works here. So I was here. So if all the comparators are off, the analog input signal must be between 0 and plus 3V plus V by 4. So the input voltage is somewhere between these two, but it will be less than this V by 4. Once the input voltage is greater than this plus V by 4, then C1 starts working. So if C1 is high, that is the computer comparator C1 is in on state and C2 and C3 are low, then the input must be between plus V by 4 and plus V by 2 volt. And if C1 and C2 are high while C3 is low, the input must be between plus V by 2 and plus 3 V by 4. And finally, if all the comparator inputs are high, the input signal must be between plus 3V by 4 and plus V volt. The comparator output levels for the various ranges of input voltages are summarized in table or figure B. So in this table, we can understand that. So when the input voltage lies between this voltage range, that means between 0 and plus V by 4, but not exceeding this V by 4, then all the three comparators, C1, C2, C3, they are all at a low position. That means they are in the off condition. They are not working. When the input voltage exceeds this plus V by 4 and less than this V by 2, then this comparator C1 only will be at a high position, and this C2 and C3 comparators will be at a low position, because the input reference voltage for this C2 is plus V by 2. That means when the input voltage exceeds this plus V by 2, then only this C2 works. And next, when the when the voltage level is between plus V by 2 to 3V by 4, then the two comparators will be in on condition. That means C1 and C2 will be in on condition, whereas the comparator 3 will be in a low condition or will be in off condition. Because this comparator C3 is in off position because its reference voltage is plus 3V by 4, and when the input voltage exceeds this plus 3V by 4, then only the C3 comparator works. So that is why up to this condition, the comparator 3 is also at a low condition or the off condition. So next, when the input voltage lies between plus 3V by 4 to this plus V, then this plus 3V by 4 is the reference voltage for this comparator 3, which was off in this in this state. And now when the voltage exceeds input voltage exceeds this 3V by 4, then it exceeds the reference voltage of C3 also, and therefore all the three comparators goes high. That means all the three comparators will be in on condition. So here just I will give one example that suppose this V is 10 volt. Suppose this V is 10 volt. Then V by 4 means it is 2.5 volt. So until the input analog voltage is less than 2.5 volt, then no comparator works. And all the comparators goes high when the input voltage is greater than 3V by 4. 3V by 4 means it is 7.5. Suppose if V is 10, 3V by 4 is 7.5 volt. So when the input analog voltage is greater than or exceeds 7.5 volt, then all the three comparators goes high. So this is how all these comparators works at a different input voltages. And the actual practical circuit diagram in the form of block diagram is shown below. So this is the complete block diagram of this 2-bit practical simultaneous analog to digital converter. So in the earlier diagram, I was shown only up to this, means the only I had shown the comparators. So that is figure A. In figure A, here we have shown only the comparators, and the extended part or the complete block diagram of this simultaneous analog to digital converter is like this. So here the output of these three comparators C1, C2, and C3 is fed to this coding network. So this coding network, what it does, it encodes the output of these comparators to make a digital signal. So that digital signal is fed back to this read gates. So these read gates are generally present at the input stage of RF flip-flops, which are used for either counting purpose or for the storage of the information. So these RS flip-flops works as resistors or the memory devices, and generally the input to these RS flip-flops is given through the gates called as the read gates. Generally, they are the AND gates, and the here this input to this RS flip-flops enters only when some logical conditions are satisfied at the input level, and hence we say that the information is read by these RS flip-flops. So these are called as the read gates. Read gates are present at this stage. And here the RS flip-flops are used to store the information or to count signal. And so we are getting here a 2-bit or digital output. So here our analog input signal is fed to the comparators. It passes through the comparators and coding network and read gates and RS flip-flops and comes out of this flip-flops as a digital signal, in a 2-bit digital signal. So this is the 2 raised to 0 bit and this is the 2 raised to 1 bit, and here we are getting the digital outputs. So this is how a complete analog to digital network of a simultaneous analog to digital converter works. And it is a 2-bit system, because you can see here 2 outputs are there, 2 digital outputs are there, digital bits are here, so it's called as a 2-bit system. And suppose if you want a 3-bit system, you will have to use the 7 comparators, and again the number of comparators goes high as the number of bits increases. So here we will see what are the advantages of this analog simultaneous analog to digital converter. The construction of this simultaneous analog to digital converter is quite straightforward and relatively easy to understand. So the circuit is straightforward and also it is easy to understand. And it is simple and is capable of extremely fast conversion rates, and hence it is called more oftenly as the flash converter. So because this flash conversion is possible for this simultaneous analog to digital converter, because of the reason that this converter uses the TTL logic, that is the transistor logic uh, in the coding network. So because of that TTL logic, the conversion rate is very high, and hence this is called as the flash converter. So these are the 2 advantages. Disadvantages of this analog to digital converters are like this. It is only useful for low number of bits, that is within 5. Means this circuit is more suitable for the applications where the number of bits are less. The reason is that as the number of bits increases, the number of comparators required or exponentially increases, that is by 2 raised to n minus 1, where n is the number of bits. So the number of comparators is the biggest problem here. So this number of comparators suddenly increases exponentially as the bit value increases. So for 2-bit, as per this formula, 2 raised to n minus 1, it is 2 raised to 2 minus 1, and this is gives the 3. So you need 3 comparators. And for the 3-bit converter, n value is 3, so it becomes 7. So that means 7 comparators are used for 3-bit. So you can see here. And for 4-bit, it is 15. So that means 15 converters we have to use. So you can see here how the number of converters is jumping exponentially. So this is the biggest problem with this and with this simultaneous analog to digital converter. And once the number of bits becomes high, the number of comparators also becomes exponentially large, and the connections becomes very complicated. So these are the drawbacks of this simultaneous analog to digital converter. So in the next class, I will go through another converter called as the counter converter. Thanks for watching.